Paleontologists thought they would find another small winged dinosaur when a fossil from 163 million years ago was first found in China's Black Shale. The scientists found something that didn't follow the rules. It had bat-like membrane wings, an extra wrist bone that no dinosaur should have, and soft tissue shadows that changed the way they thought about how flight evolved. In the blink of an eye, one specimen made experts question every date, every theory, and every accepted way that dinosaurs became birds. Not only was it strange, but it was also a scary warning that evolution has a lot more secrets than we thought, and some of them are much stranger than we thought. The reveal in Black Shale. The lab was very quiet when the slab first broke open. It was the kind of silence that makes scientists forget to breathe. They saw more than just a skeleton in the Black Shale that was 163 million years old. They could see the ghostly shape of soft flesh that had been pressed into it. It looked like the animal had put down its bones yesterday instead of in the Middle Jurassic. The bones were very small and fragile, and they were perfectly organized. Paleontologists were shocked by the dark shapes around the arms though, edges spread out, curves that are smooth, a circle that goes from the wrist to the side. This wasn't the fluffy shape you see in remains of early birds. There was something else here that was scary. A membrane wing that was kept so well that it looked like it was written on the stone. At first, the team thought they might be misreading a trick of the shale or an artifact of decay. Soft tissue impressions are rare enough. But this was more than an outline. It had structure, layers, attachment points. You could follow the membrane around the forearm, trace where it anchored to the body wall, and see how it thinned toward the end, just like in bats or pterosaurs. Except this creature wasn't a bat, and it definitely wasn't a pterosaur. It was a dinosaur. And that meant something paleontologists had been teaching for decades, that dinosaurs only evolved feathered wings, suddenly cracked open like the shale in front of them. The first shock came from the overall shape. The membrane stretched not just between arm and body, but also forward toward the wrist, in a way that felt familiar to anyone who had studied pterosaurs. But the skeleton didn't match pterosaurs at all. The fingers weren't elongated like a pterosaur's wing finger. There was no long, stiffened fourth digit. Instead, the forearm bones themselves were unusually long and delicate, almost as if the entire arm was designed to stretch the membrane outward. This wasn't one of the known flight styles. It was something in between, a structure with no modern equivalent. Another creepy thing was how clear the carbon film was. A lot of well-known fossils from the Yanliao biota still show feathers, skin, gut contents, or the shape of muscles. But this wasn't like that. In this case, the membrane didn't look like a random spot or light color change. Its edges stood out against the rock like a knife. Paleontologists could even see small differences in thickness, which suggests that there were stronger spots where stress would have been highest during flying. This wasn't the jumbled form of a body that was falling apart. This was the shape of a wing that used to work in real life. The level of preservation also pointed to unusual conditions. The Black Shale formed in a quiet, oxygen-starved lake bed, where bodies sank into fine sediments and decomposed slowly. Without oxygen, scavengers couldn't reach them, and the decay process left behind delicate chemical films. For feathers, this was perfect. But membranes? Membranes almost never survive unless conditions are nearly ideal. That made this fossil feel like winning the lottery, but with stakes much higher than wealth. It meant scientists were looking at a flight system they didn't know dinosaurs had. It wasn't that the monster had a membrane that was alarming. It was that the membrane lived with filaments, which are small structures that look like hairs and run along the body. There were no known rules for this mixture. The membranes of pterosaurs were clean. The feathers of birds were clean. This fossil threw off the divisions. Paleontologists had to accept that their mental model of how dinosaurs evolved was too simple, because it was a hybrid that fit in the middle. Meet the culprit, Ambopteryx longibrachium. At first view, Ambopteryx longibrachium would have seemed harmless. It was about the size of a chicken, had feathers, was light, and lived in the woods of what is now northeastern China in the Middle Jurassic. But as soon as paleontologists laid out its bones, they knew this little animal wasn't just another small dinosaur that lived in trees. It felt disturbing that the size of it wasn't right. Its forelimbs were way too long for its body. Its wrist bones were made strangely, and its fingers were stretched way past what regular climbing dinosaurs needed. Even before the soft tissue prints proved it, the skeleton looked like it was built to hold out a membrane, a wing membrane, when looked at as a whole. The Ambopteryx was very small, but its body was clearly an experimental flight system. The name says a lot. Longibrachium literally means long arms. And those arms weren't long because it hunted or dug or grabbed prey. They were long because they were the framework of a gliding surface. The ulna and radius were elongated and slender, more similar to the stretched forelimbs of bats than to the robust arms of typical theropods. The fingers were even stranger. One finger, in particular, was extended and reinforced, almost like it was meant to anchor tension from a wing membrane. These proportions immediately made Ambopteryx the second confirmed member of a bizarre dinosaur group called Scansoriopterygids, tree climbing, membrane-winged dinosaurs that looked like evolutionary experiments halfway between birds, bats, and pterosaurs. Its claws also told an important story. They were strongly curved, sharp, and powerful for its size. CT studies of the arm bones show thickened areas where flexor tendons are anchored, indicating a lifestyle of constant gripping. Not running, not digging, but climbing vertical surfaces. Ambopteryx wasn't a ground bird. It was a dedicated climber, a creature that moved through the trees like a mix between a squirrel and a woodpecker, gripping bark and scrambling upward to launch into glide paths between trunks. Everything about its skeleton suggests height was safety, height was opportunity, and height was the only way its strange wings made sense. The most unusual thing about Ambopteryx's body plan was how it mixed parts of different developmental paths. In order to fly, it didn't use its feathers as its main surface. They were thin, thread-like, and looked more like insulation than mechanical tools. They covered the body in pieces, maybe to keep it warm, or just to show off. It did have wings, but they were not winged. A patagium, which was a sheet of skin stretched between the long forelimbs and the body, was its main lift surface. That combo was shocking on its own. It was thought that dinosaurs could only fly with furry wings. Ambopteryx didn't follow the rules. Its tail was another important part. In contrast to early birds, Ambopteryx had a short, stiff tail with joined vertebrae, which is similar to a pygostyle and is meant to support tail feathers used for moving. However, Ambopteryx did not move with its wings. It's possible that the joined tail helped it stay in the air while the membrane stretched between its arm and body caught air. The fact that this dinosaur had a tail structure that looks like feather control and a wing structure that is mostly membranes shows how odd it really was. The one half of its body pointed to the bird lineage, and the other half pointed to a dead end in how species evolve. The internal anatomy hinted at its lifestyle too. Bone histology from the fossil shows relatively slow growth and a lightweight skeleton, traits common in animals that prioritize agility over power. Its ribs and shoulder girdle were built to allow wide spreading of the arms, like raising and tensioning a living parachute. And unlike many small theropods, Ambopteryx had a lightly built torso with enough space for strong climbing muscles, but not the deep keel needed for full flapping flight. It wasn't a flyer, it was a glider that used momentum and gravity more than muscle, the styloform shock. Scientists looked at Ambopteryx's wrist in great detail for the first time and saw something much scarier than a cute little glider. They saw a dinosaur wrist bone that didn't belong there. A long, thin, rod-like structure stuck out straight from the side of the wrist. This structure didn't look like it came from any known dinosaur. No, it wasn't a finger. It wasn't a broken bone. It wasn't a shadow of cartilage. That thing was completely different. A styloform element, a special strut used to hold up a wing membrane. The fossil went from being weird to being evolutionary nightmare fuel at this point. Styloform elements are not normal dinosaur features. In modern animals, they appear in exactly two groups: bats and flying squirrels. In bats, the styloform helps hold open the trailing edge of the wing membrane, preventing collapse during flapping. In flying squirrels and colugos, the styloform extends the gliding membrane like a tent pole. In pterosaurs, the role is handled by the elongated fourth finger, not a separate rod. A dinosaur with a styloform meant that dinosaurs independently invented a third membrane wing system that looked nothing like birds and nothing like pterosaurs. It was an entirely new experiment in flight, one that scientists had never predicted. The bone itself looked almost artificial. Long, slender, smooth and stiff. It projected sideways like a built-in glider pole. CT scans showed it had a bony core with vascular canals, meaning it was alive, growing tissue, not a piece of cartilage or a fluke fossil artifact. It also had a strong articulation point on the wrist, showing it wasn't loose or misplaced. It was meant to be there. The joint surface was reinforced, which meant the styloform supported tension from the membrane and handled aerodynamic load. Ambopteryx wasn't just gliding on stretched skin. It had a skeletal wing frame, something closer to bat engineering than dinosaur engineering. That's what scared paleontologists most. If dinosaurs could evolve a styloform once, they could have done it multiple times. It meant the dinosaur family tree didn't just experiment with feathers and proto-wings. It may have produced whole branches of membrane wing forms that left little or no fossil record. The styloform wasn't a minor tweak, it was a major structural adaptation. Evolution doesn't accidentally grow a new limb-like bone. It requires genetic retooling, developmental pathway shifts, and biomechanical integration. It meant Ambopteryx wasn't a playful side note. It was evidence of a serious evolutionary attempt at a new type of flight. Another unsettling thing was that the styloform didn't look like any early bird's body. The glide membrane went far past the arm, which was much longer than expected for a dinosaur that size. When scientists tried models in the shape of wings, they found that the membrane would fold inward without the styloform. When the styloform was in place, the wing got a wide, triangular surface that was perfect for short, controlled swings between tree stems. This wasn't sloppy evolution, it was exact engineering, like the way the bones are arranged in animals that live mostly by sliding. Furthermore, it was where it was put. The styloform helps bats hold the back edge of their wings. It's close to the elbow of flying squirrels. In Ambopteryx, it stuck out from the wrist, making a wing with a completely different shape. This shape isn't used by any animals today. That means dinosaurs didn't copy bats or squirrels. Instead, they came up with their own version, which was more efficient. If something doesn't work, evolution doesn't like to do it again. The styloform showed that this way of flying worked well enough for at least two known species to keep using it: Ambopteryx and Yi Chi. Wait, dinosaurs. Did bat wings? For more than 100 years, the story of how dinosaurs flew seemed simple and reassuring. Feathers first evolved for warmth, then for show, then for gliding, and finally for full swinging flight. The end result was birds, and everything led in that way. Then Ambopteryx and Yi Chi showed up, and paleontologists had to face something that seemed almost impossible. Dinosaurs developed wings like bats. Not wings with feathers. Not early wings. Real membranes stretched across long arms that were held up by a styloform rod. In the dinosaur family, there was a second, parallel flying system. It was like finding out that whales tried to become bats at one point in time. What made this discovery so mind-bending wasn't just the structure, but the timing. Membrane flight was supposed to belong to pterosaurs, the masters of skin-wing aerodynamics, and later to bats. But dinosaurs? Dinosaurs had always been locked to the feather wing path. The idea that they could branch out and build something completely different wasn't just unexpected, it felt like a violation of the rules. And science had to swallow a hard truth. Evolution doesn't follow rules, it follows opportunities. The wing of Ambopteryx was nothing like a bird wing. Bird wings are built from feathers extending from a strong arm and hand. Each feather can adjust its angle to fine-tune airflow. Membrane wings, in contrast, are soft, stretchy, and behave more like parachutes than fans. They give glide efficiency, but limit precise control. And in Ambopteryx, that membrane didn't connect to the fourth finger like a pterosaur's wing. Instead, it stretched between the arm, the body, and the styliform rod. A Frankenstein hybrid of bat, glider, and pterosaur geometry. No modern creature has anything like it. The best way to understand how shocking this is, let's say someone told you that lions used to have flippers and lived like seals for a short time. When you looked at the skeleton and the lion family tree again, your brain would start to bend. That's how shocked paleontologists were. This wasn't what dinosaurs were meant to do. They did though. Even more unsettling was what this meant for the forest ecosystems of the Middle Jurassic. Before these fossils, the mental image was simple. Pterosaurs ruled the skies, while early feathered dinosaurs hopped around the underbrush, too primitive to compete. But now we know that in the same forests where early bird-like dinosaurs were evolving feathers for gliding, other dinosaurs were experimenting with membranes instead. It wasn't a clean ladder, it was a crowd of competitors, all racing toward the same goal, controlled aerial movement using completely different strategies. A further fascinating development is that winged dinosaurs were already living in the area when Ambopteryx lived. That means membrane-winged dinosaurs weren't primitive side trips from the main path. They lived at the same time. They went up and down the same trees, searched for the same bugs, avoided the same dangers, and flew through the same trees. Evolution wasn't slowly switching from membranes to feathers. In the same forest, both methods were used at the same time. That alone forced scientists to rewrite textbooks. Before this, feathers were considered the superior or more advanced solution for dinosaurs. But Ambopteryx proved that membranes weren't a desperate attempt. They were a deliberate design, one with structural supports and aerodynamic adaptations. These dinosaurs weren't copying bats or pterosaurs. They independently invented their own membrane system millions of years before bats ever appeared. It's one thing when evolution repeats itself. It's another when it repeats itself in completely different lineages, in completely different ways. Biomechanical models show that Ambopteryx probably wasn't a good flyer. Instead, it was probably a quick floater. That didn't make it less amazing. Flying isn't black and white. It was helpful to be able to glide silently between branches in thick Jurassic woods. With membrane wings, it can take off quickly, turn slowly, and rest quietly. It wasn't in need of moving power. It had to be able to move from one tree to another without hitting the ground, where predators were waiting. It also had to be able to hide and be controlled. Before Ambopteryx shocked scientists, there was Yi-Chi, a small dinosaur about the size of a crow that paleontologists didn't know what to do with. The fossil was definitely strange. It had long arms, a wrist bone that looked like it was stretched out too far, and weak signs of a structure that looked like a membrane. But it was so strange and not at all like what scientists thought dinosaurs would do that many didn't believe what it seemed to show. Some people thought the membrane was a sign of decay. Some people thought the styliform rod was a bone that had moved. Some people even thought the fossil might have been deformed by being pressed together. To sum up, Yi-Chi was the first warning sign, but most people in the field decided to ignore it. On the slab, Yi-Chi looked almost innocent. Its skeleton was delicate, lightweight and shaped for climbing, much like a Scansoriopteryx guide should be. But when scientists began mapping the soft tissue shadows around the forelimbs, the outlines didn't match the fringe feathers expected in small theropods. Instead, the impressions were smooth, sheet-like, and sharply defined. They didn't resemble proto-feathers at all. They looked like patagia, skin membranes. But at the time, the idea of a dinosaur with a bat-like membrane seemed too extreme, and paleontologists spent months questioning whether this interpretation was even possible. Then there was the styliform rod. It projected from the wrist like a thin spike, longer than some of the hand bones. CT imagery revealed it was a genuine bone, not cartilage, and not a flattened finger. But its position was so bizarre that researchers struggled to imagine it in life. Why would a dinosaur evolve a stiff rod jutting sideways from the wrist? The idea of a membrane support structure, a styliform, was proposed early, but even the scientists describing the fossil admitted the structure didn't neatly fit any known aerodynamic system. Critics argued it was too slender to support real flight loads. Supporters pointed out that flying squirrels use even thinner styliforms. The debate became a tug-of-war between expectation and evidence. Part of the skepticism came from the fossil's extreme rarity. No other dinosaur had anything like this. When a single specimen shows unexpected features, paleontologists approach carefully. They check for taphonomic distortions, breakage, or misleading soft tissue halos. Some early comments suggested the membrane was simply stretched skin from decomposition. Others argued the styliform could be a broken rib that shifted during burial. These ideas weren't unreasonable. They were attempts to fit Yi Qi into the existing evolutionary picture. But in trying to stay cautious, many scientists underestimated what the fossil was actually telling them. Dinosaurs had tried membrane wings. People used to try to make a straight line between dinosaurs and birds, which is another reason why Yi Qi was forgotten for years. Everyone knew the story about the feathered wings. Membrane wings made that story more complex. And in science, you need more proof for claims that seem too strange to be true. Yi Qi was in a strange place. It wasn't pushed away, but it also wasn't fully accepted either. It was talked about in articles as an interesting fact, but with caveats like if the wing membrane is correctly interpreted, or pending further specimens. It was weird for everyone. Not many people were ready to say that it changed the rules. Then came Ambopteryx. When another Scansoriopteryx turned up with the same styliform rod, similar wing membrane impressions, and even clearer anatomical context, the field could no longer treat Yi Qi as an outlier. With two specimens from the same region showing the same bizarre features, the membrane wing interpretation jumped from possible to undeniable. Suddenly, all the questions Yi Qi raised had concrete answers. The styliform wasn't a fluke. The membrane wasn't decay. The system wasn't a misinterpretation. It was real, functional, and preserved in multiple individuals. This retroactively changed how paleontologists understood Yi Qi. Its weirdness was no longer an obstacle, it was a clue. Details that once seemed confusing now formed a coherent aerodynamic strategy. The long forelimbs, the styliform, the soft tissue films, the skeletal proportions. They all aligned with a gliding lifestyle. The membrane didn't replace feathers entirely. It complemented sparse filaments in a hybrid system unlike anything alive today. The acceptance of Yi Qi also showed us something humble about paleontology. Amazing fossils show up before we can figure out what they mean. The wrist, the membrane, and the measurements were all signs from the start, but it didn't feel safe to change the evolutionary maps without Ambopteryx. Once the second fossil showed up, Yi Qi went from being a strange individual to being a key part of a dinosaur flight project that was tried and failed long before birds took over the sky. How old is old? The 163 million AD timestamp. Not the membrane wing itself that made paleontologists jump for joy, it was the date that was carved into the rock that held it. In the Tiaojishan Yanliao Formation, remains of Ambopteryx and Oigui were found. This is a group of sediments that has been radiometrically dated to 163 million years ago. That number really hit home because it put these dinosaurs with membrane wings way back in the Middle Jurassic, a time when most scientists didn't think dinosaurs had even begun to build complex flight systems. Flyers with feathers? Yes, but a long time later. A lot of gliders? Perhaps, but not if they had skin wings. It was not only strange to find a dinosaur with a styloform-supported patagion in the Middle Jurassic, but it was also out of place, like discovering a smartphone in a castle in the Middle Ages. The dating wasn't guesswork. It came from uranium-lead analysis of volcanic ash layers sandwiched between the fossil-bearing beds. These thin ash sheets act like timestamp pages in a prehistoric book. When isotopes inside the ash decay at known rates, scientists can pinpoint when the eruption happened, and therefore constrain the age of the fossils above and below it. Multiple labs tested these ash layers from different locations within the Tiaojishan sequence, and they all converged around the same number, 163 to 159 million years old. That meant there was no wiggle room. These animals lived tens of millions of years before Archaeopteryx, the first bird, ever flapped its feathered wings. This timing flipped the story of dinosaur flight on its head. Before these fossils were described, the dominant model was that flight-related features evolved slowly in the late Jurassic, with feathers taking priority as the main aerodynamic surface. Protobirds, like Anchiornis and Archaeopteryx, were believed to represent the first real steps toward gliding and powered flight. But Ambopteryx and Yuishi forced scientists to reconsider the entire sequence. Feathered wings were not the first flight experiment. The Middle Jurassic forest canopy was already buzzing with aerial dinosaurs using a completely different approach. What made this especially shocking was that pterosaurs were already masters of the sky by 163 million years ago. They had been flying for tens of millions of years before these Scansoriopterygids even appeared. So why would dinosaurs evolve membrane wings independently if pterosaurs already dominated aerial niches? The answer lies in the ecosystem. The Yanliao forest were dense, vertical environments. Tall conifers, cycads and ginkgo-like trees formed layered habitats with narrow gaps between trunks. Pterosaurs were adapted for open air and long-distance flying, not tight gliding among tightly packed trees. The Scansoriopterygids took advantage of this. Their membrane wings were engineered for short, controlled hops between branches, something pterosaurs were too large and too specialized to do. This realization pushed paleontologists into uncomfortable territory. If dinosaurs were experimenting with flight this early, then the early evolution of feathers might not have been about flight at all. Instead, feathers may have evolved for insulation or signaling first, and membrane systems were an early aerial shortcut that branched off temporarily. The Middle Jurassic timestamp forced researchers to confront the possibility that feathered wings were not an inevitable evolutionary outcome. They were simply the version that survived. In a creepy way, the fossil beds themselves said something. The Yanliao biota is known for having very good preservation, which means that we can see soft tissues and sensitive structures that wouldn't fossilize in other places. If membrane-winged dinosaurs lived in places other than this, their wings might not have been found in places with few fossils. That is, Ambopteryx and Yiqi might not have been very rare. They might just have been the only ones whose wings have been preserved. 163 MR is more than just a number. It's a warning that fossil records favour the people who are kept alive over the people who lived. The timestamp also shifted how paleontologists think about the early bird family tree. Before these discoveries, the Middle Jurassic was assumed to be dominated by ground-running coelurosaurs and early feathered theropods that had not yet entered the trees. But Ambopteryx shows that at least one dinosaur lineage was already deeply arboreal, climbing trunks with curved claws and using membrane-assisted gliding long before feathered wings fully evolved. It moved dinosaurs into the trees earlier than anyone expected. Soft tissue, hard truths. When paleontologists looked past the Ambopteryx bones and noticed the ghostly shadows around them, they knew they weren't seeing the normal, pretty preservation that can be found in fossil beds. They saw a lot of scary details in the soft tissue. Carbonized films that showed the exact edges of a flight membrane, thin filaments running along the body, and weak signs of connective structures that shouldn't have been there after 163 million years. These were not smudges or marks from decay. They looked like scary plans of bodies pressed into rock. Once scientists agreed that the dark halos were really membranes, it became impossible to simplify the story of how early dinosaurs flew. Soft tissue fossils are notoriously rare. Skin rots, membranes collapse, proteins break down, and scavengers destroy delicate structures long before they have a chance to fossilize. But the Yanliao beds created perfect conditions for preservation: still water, fine sediment, and near-zero oxygen. When a small dinosaur sank to the bottom, it lay undisturbed long enough for thin films of organic material to imprint themselves into the mud. Over millions of years, those films transformed into carbon. In most fossils, these films hint at feathers or simple outlines. But in Ambopteryx, they captured something much more complex: the geometry of an entire aerodynamic system. Under magnification, the membrane impressions show subtle gradations. Near the arm, the film is thicker and darker, suggesting stronger connective tissue where tension was highest. Farther out, the membrane becomes thinner and lighter, matching what we see in gliding mammals and pterosaurs. These distinctions matter because they prove the membrane wasn't accidental. It was built for stress distribution. If the silhouette had been produced by skin collapse or decay, the film would be uneven, wrinkled, or blotchy. Instead, it preserved a clean aerodynamic arc. The membrane had shape, it had structure, it had a purpose. The biggest surprise was how the membrane attached to the body. It didn't simply stretch from wrist to torso in a loose sheet. The carbon imprint forms a curved leading edge along the forearm and a smooth trailing edge toward the hip region. This attachment pattern matches models of efficient gliding patagia seen in flying squirrels and colugos. A membrane that only connected at the arm would flutter uncontrollably. A membrane that anchored along the body created stability. Ambopteryx had the latter, proof that its flight system wasn't sloppy or experimental. It was a refined design. The small filament marks that were still there near the shoulders and tail were another shocking feature. It wasn't a flight feather. These short, hair-like structures were called dinofuzz, or protofilaments. Some of them were stiff, and some were fluffy. The fact that they were there proved that Ambopteryx had two different skins: a soft coat for warmth and a stretch membrane for moving. This is something that no current airplane has. Flying squirrels have fur, but they don't have a styliform rod. Bats have coverings on their wings, but no fuzzy stuff to keep them warm. Ambopteryx took traits from different ecosystems and put them together to make an animal that looked like it was put together from different pieces. Histological studies revealed more unsettling truths. Thin sections of the styliform and arm bones showed thickened zones for tendon attachment, meaning the membrane wasn't passive. It was actively controlled. Ambopteryx could tension it, alter its curvature, and adjust glide angles mid-air. This moved the creature out of the category of accidental glider and into the realm of engineered flight, even if limited. The membrane was a functional aerodynamic surface, not a loose flap of skin. When paleontologists tried to accept the truth about this soft tissue, it was one of the hardest things for them to do. For many years, feathers were thought to be the only way to get to flight, but the carbon layers around Ambopteryx made it seem strange. Here was a dinosaur with fur, but no feathers on its wings. It was the membrane that stood out. That meant feathers weren't the only way to get into the air. They were only one choice among many. At least one branch of dinosaurs went a completely different way and disappeared before the time of birds. Two wing systems in one forest. One of the most disturbing things that the Yanliao fossils showed us was that the Middle Jurassic skies weren't just a simple order with pterosaurs at the top, dinosaurs at the bottom, and early birds slowly moving up the evolutionary ladder. Instead, those woods were a crowded battleground in the sky where three different types of wings worked together. Feathered proto-wings, pterosaur skin wings, and the newly found membrane-assisted wings of Scansoriopterygids. Three separate flying tests were done next to each other, flapping and floating through the same old canopy. Paleontologists used to think that dinosaurs only learned to fly once, but this environment proved them wrong. The forests themselves were dense, towering and stratified. Conifers reached high into the air, spreading out umbrella-like branches, while ginkgos, cycads and ferns filled the lower levels. This vertical complexity created a perfect environment for small animals to leap, glide and maneuver. But it also created intense competition. The canopy wasn't empty, it was prime real estate. Every layer of the forest offered different food sources, hiding spots and perches. In such an environment, mobility wasn't optional, it was survival. And mobility took many forms. Pterosaurs, the oldest and most established flyers, dominated the open spaces above and between the tallest trees. Their long wings, supported by an elongated fourth finger, were designed for efficient flight across long distances. They weren't agile among branches. Their wingspan alone made that impossible. They soared, they cruised, and they fed in open air. They owned the sky, but not the canopy. Feathered dinosaurs, early Paravians and their relatives, occupied a different aerodynamic niche. Their proto-feathers allowed for parachuting descents and short glides. They weren't powerful flyers yet, but their feathered limbs provided a combination of drag and lift. They could launch off branches and steer themselves with tail feathers, using flapping-assisted hops to move between levels of the forest. Their aerodynamic strategy relied on surfaces that could be adjusted feather by feather, giving them control even if their lift was limited. Then came the Scansoriopterygids, the membrane-wing gliders like Ambopteryx and Yiqi. They weren't built for long distances like pterosaurs or for detailed feather control like early birds. They occupied the middle space, literally and ecologically. Their stiffened membranes allowed for silent, stable gliding between trunks in tight canopy tunnels. In the spaces where pterosaurs couldn't turn and feathered dinosaurs couldn't generate enough lift, the membrane-winged dinosaurs thrived. Their wings didn't need precise articulation. They needed surface area and tension, something their styloform rods and extended forelimbs provided in spades. This three-system coexistence is what shook paleontologists. It meant dinosaurs didn't develop flight in isolation. They developed it under pressure. They developed it while competing with two other aerial strategies that were already well established. It wasn't a slow march toward bird flight. It was a desperate evolutionary scramble in a forest filled with aerial traffic. The Scansoriopterygids weren't slow learners, they were innovators. They built a system that worked for their specific ecological slot. The fossil evidence supports this coexistence strongly. Pterosaur remains appear in the same rock formations, showing that gliders shared the skies with experienced flyers. Feathered dinosaur fossils, especially early Paravians, also appear in the Yanliao deposits, meaning the membrane-winged forms weren't filling a temporary empty space. They were in direct competition with birds in the making. The presence of three aerodynamic systems in one environment is not only rare in the fossil record, it is almost unheard of in modern ecosystems. Today, we have only two main flight systems among vertebrates: birds and bats. But 163 million years ago in China, the forest canopy was a technological testing ground where evolution ran simultaneous experiments. Grip like a gecko, launch like a squirrel. Not the wings, but the hands, fingers and claws are one of the most telling parts of Ambopteryx and its sister species with membrane wings. These animals didn't fly through the air like pterosaurs did, and they didn't flap their wings to get across gaps like early birds do. Their whole body plan shows a different story. They were climbers who were made to live on tree stems. And knowing how they live changes how we think about their strange flight system. They didn't have wings for speed or height. They had wings for short, precise jumps between trees, which is the kind of movement that only animals that live stuck to the forest walls needed. Start with the claws. Scansoriopterygids had sharply curved, recurved claws shaped like hooks more than cutting tools. Modern animals with similar claw curvature include geckos, climbing rodents, and some tree-dwelling marsupials. These aren't traits for ground runners or long-distance flyers. They're optimized for gripping bark, hugging rough surfaces, and holding on even when the body is at odd angles. Their hands were proportionally large for their body size, and the fingers were long and slender, giving them a wide grip range. That means they could press against uneven surfaces, cling to vertical trunks, and pivot their bodies to choose the best launch angle. The forelimbs themselves were extremely long for such a small dinosaur. In Ambopteryx, the forearm bones were nearly as long as the legs, a proportion not seen in any early bird or ground-based dinosaur. This detail matters because long arms help animals distribute weight while climbing. They can stabilize their bodies as they shift vertically, and those same long limbs become the frame that supports the membrane wing when they leap. These proportions suggest a dual purpose: secure climbing and controlled gliding. The bones were lightweight but strong, a signature feature of animals built to handle repeated leaps. They weren't hollow like modern bird bones, but CT scans show thin walls and internal reinforcing patterns that reduced weight while still surviving impact. In arboreal animals, bones must endure sudden drops, slips, and rapid turns. Ambopteryx fits that pattern perfectly. It wasn't fragile, it was agile. The tail is an extra piece that completes the picture. It wasn't long and bendy like a balance stick. It was short and stiff. That means it wasn't used to help people run. Instead, a stiff tail keeps the animal stable while it climbs and glides. It stops the body from moving in any other way, so it can't twist in the air. Think of a flying squirrel opening its wings. The tail doesn't really steer, but it keeps the body from moving. Most likely, Scansoriopterygids used the same trick. Think about where it all began now. A small animal sitting on a tree trunk doesn't take off like a bird does from a branch. Instead, it pushes outward and slightly lower, making a path for the first slide. Because it has a smooth, quick surface, the membrane catches the air much faster than feathers would. In other words, a Scansoriopterygid didn't need to have strong chest muscles or flap its wings quickly. It only took a strong grip, a burst of leg power, and a membrane that stiffened into shape as the styloform rod stretched to control the glide. Biomechanical models suggest these dinosaurs likely crouched, dug their claws into bark, pushed off, and instantly spread their arms wide, a launch more similar to a sugar glider or a colugo than to a bird. The glide wasn't long, but it was silent and smooth. Insect prey or small vertebrates on nearby branches wouldn't hear the approach until it was too late. Their lifestyle would have centered around stealth, short bursts of movement, and precise control through the mid-canopy. Glide models equals pure chaos. Scientists first tried to figure out how Ambopteryx and its cousins with membrane wings move through the air. The results were so confusing and contradictory that one scientist joked that the animal looked like it was designed by a committee that never met. The shapes of birds or pterosaurs' wings make them easy to figure out in terms of aerodynamics. But Scansoriopterygid's wings were biological problems. There was no clear, expected way for them to fly, even though they had long arms, a wrist rod, soft tissue coverings, small bodies, and climbing claws. And things got even more crazy when early glide models were made. Flying squirrels, birds, and pterosaurs were not like these dinosaurs. These dinosaurs did not swing, flap, or rise. They did something in the middle, something unsteady, risky, and very strange. One of the first challenges was reconstructing the actual membrane. Fossils preserve thin carbon films outlining where skin stretched along the limbs, but those outlines don't tell scientists the tension, thickness, or elasticity. That means aerodynamic teams had to guess, sometimes assuming a tight, bat-like membrane, other times a loose, parachute-like one. But no matter which shape they tried, the glide simulations kept producing the same frustrating result. Ambopteryx didn't fly well in open space. Its stability dropped quickly once it left the forest canopy, and without strong flapping muscles, it struggled to maintain lift in long glides. So if it wasn't built for long glides, could it at least maneuver well? That's where the models became even more chaotic. Some reconstructions produced decent turning ability thanks to the stretched membrane across the arms and torso. Others showed that the stiff styloform rod limited bending, making tight turns difficult. One study found that shifting the body posture even slightly altered the glide path dramatically, meaning the animal needed instinctive micro-adjustments to avoid crashing. The membrane wing system worked, but it demanded precision. The animal had to pick its launch points carefully, judge distances accurately, and rely on the forest structure itself to survive. Wind was another problem. In modern gliders like squirrels or colugos, the membrane can flex in gusts, helping stabilize the animal mid-air. But a styliform-supported wing doesn't flex easily. Simulations of crosswinds showed that a poorly timed gust could tilt Ambopteryx sideways or push it off course. The only way this animal could use its wings reliably was by gliding short distances, ideally between stable, vertical surfaces like tree trunks. In these tight spaces, wind was reduced, distances were predictable, and the membrane only needed to control a brief descent rather than a full glide. Yet despite all these difficulties, glide models show one consistent strength: initial lift. The moment Ambopteryx pushed off a branch or trunk, the membrane snapped into shape instantly. Feathers take time to align. Pterosaur wings needed more force to fully extend, but a membrane stretched over long arms and braced by a styloform rod. It delivered immediate lift with almost no energy cost. That gave the animal a crucial advantage in ambush hunting. It could go from stillness to airborne in a heartbeat, silently, without a flapping takeoff that might scare prey. Why this was terrifying, scientifically. Researchers weren't just excited when they learned about the full implications of Ambopteryx and its membrane-winged relatives. They were more scared. Not fear of the animal itself, but fear of what it did to careful stories about evolution that had been told for decades. Paleontology is more than just finding bones. It has to do with trends, bloodlines, and figuring out how one big change leads to the next. Flight in dinosaurs had a clean, satisfactory story for 150 years. Feathers started out as a way to keep warm, then turned into tools for showing off, then became flying surfaces, and finally turned into full wings. It was a straight line from small theropods to birds. Simple, beautiful, and full. It then came along and blew a hole right through that building. The first terrifying thing was the timing. This wasn't a late Jurassic or early Cretaceous oddball experimenting with flight after birds had already appeared. This was middle Jurassic, roughly 163 million years ago, right in the period when early Paravians were just starting to refine feathered gliding. That meant dinosaurs weren't developing flight along one single pathway. They were exploring multiple aerodynamic strategies at the same time, in the same forests, under the same pressures. This parallelism clashed with the old linear model and forced scientists to rethink everything from the origin of feathers to the definition of pre-bird. Then came the styloform element, an extra rod-like structure projecting from the wrist to support a membrane. Nothing like it existed in any other dinosaur. It wasn't a stray bone or taphonomic artifact. It was real, jointed and vascularized, and it proved that dinosaurs on their own invented a wing system completely separate from the feather-based system that led to birds. For researchers who believe feathers were the only pathway dinosaurs ever used to achieve aerodynamic control, this was a direct contradiction. If dinosaurs could evolve bat-style wings, even briefly, then the one-solution-fits-all view of dinosaur flight collapsed. The fact that the membranes were still in good shape was another disturbing thing. Amazingly clear carbon layers outlined the patagium, or wing membrane, in fossils from the Yanliao biota. It wasn't just guesswork in the form of hazy spots of soft tissue. The marks showed exactly where the connection points were on the arms and body. They even kept the filament-like fuzz around the edges of the body. The soft tissue clarity left no room for interpretation. The skin-supported wings of Scansoriopterygids were very complicated and worked very differently than feathered wings. It wasn't a shift. It wasn't only partly evolved. It was a full setup that worked. In a worrying way, this made me wonder how many other flight tests we have missed. Soft tissue structures and fossils are very hard to find. How many older or similar forms of membrane-winged dinosaurs lived somewhere else but left no fossils? 2 have lived long enough to be fossilized in this one area. Did different groups of dinosaurs try out different wing shapes? Did some testing with sheets that look like parachutes? Feathered gliders and membrane gliders may have been competing for the same places. The fossil record isn't very complete, and Ambopteryx showed how many holes there might be that hide dead ways of flying. The discovery also terrified paleontologists because it exposed bias in scientific expectations. For decades, anything that didn't fit the clean feather-to-bird narrative was dismissed as an artifact, a misinterpretation, or a one-off mistake. When Yi-Chi was first described, the styloform element and membrane traces were so bizarre that some researchers simply waved them away as odd taphonomy. It wasn't until Ambopteryx matched the anatomy point for point that the field was forced to acknowledge the truth. Evolution produced weird solutions, and our tidy frameworks had ignored them. The colour question. In geology, colour is one of the things that is hardest to figure out. Bones are easy to fossilise, but colours, almost never. So, when scientists studying Ambopteryx and other Scansoriopterygids found what looked like preserved melanosomes, microscopic cells that carry pigment, it opened a door no one saw coming. Scientists weren't just trying to figure out the shapes of wings and how they would have glided. They were also trying to picture what one of the strangest dinosaurs ever found would have looked like. What we knew about these creatures made them even scarier. Their membrane wings were probably dark, maybe even black, and their bodies had a soft fuzz that might have been a mix of subtle browns or charcoal tones. This plane wasn't flashy or bright. It was a thing that lived in the dark. Melanosomes are tiny capsules inside cells that hold pigments like eumelanin and pheomelanin. In modern animals, their shape correlates strongly with colour. Long, sausage-shaped melanosomes often produce blacks and dark browns. Round ones lean toward reddish or lighter hues. When paleontologists dissolved small samples from the soft tissue outlines of Scansoriopterygid fossils, they discovered melanosomes arranged in patterns matching modern dark membranes. That means the wing wasn't pale or translucent, like bat skin. Instead, it likely absorbed light, reducing reflection, a trait common in nocturnal or crepuscular gliders. This matches well with what biomechanical studies suggest about Ambopteryx. It wasn't flying in open skies, but weaving through dense forest canopies. In those dim environments, dark wings would make it harder for predators to spot the animal as it moved between branches. And for a creature that relied heavily on stealth for ambush hunting, any advantage in remaining unnoticed would be crucial. Colour, in this context, becomes as important as wing structure. The fuzz covering parts of the body also revealed pigment clues. These filament-like structures weren't true feathers, but served a similar purpose: insulation and possibly camouflage. Melanosomes inside these filaments pointed toward darker, earth-tone colours. Not flashy, not patterned. More like the colour schemes of modern gliding mammals that hide in tree hollows. Animals like sugar gliders and colugos, which rely on being invisible until they launch. Ambopteryx may have shared that same survival strategy. Some researchers, however, raised a provocative alternative. Dark membranes can also be used for display, especially in low light, where a sudden flash of contrast can signal territory or attract mates. If Scansoriopterygids lived in social groups, something their anatomy doesn't rule out, the membranes could have doubled as visual signals during close-range interactions. A quick raise of the arms might reveal a shiny, dark surface that stood out in twilight. The idea is speculative, but the anatomical possibility exists. There is also the question of structural colour, colours produced not by pigments, but by microscale patterns that scatter light. While there is no direct evidence of structural colour in Scansoriopterygids, some paleontologists note that the texture of the membrane impressions shows ridges and folds. If these patterns were once supported by collagen fibres or other repeating structures, they might have influenced how light bounced off the wing, giving it a matte or semi-reflective sheen. Even without bright hues, such surfaces could create distinctive visual effects. Another unsettling detail emerged from comparing melanosomes in Scansoriopterygids to those in early birds from the same region. Early feathered dinosaurs often had a mix of light and dark patterns, sometimes even stripes or bands. But the membrane-winged forms show almost no evidence for varied colours. Their palette seems narrow, suggesting they were adapted to a very specific ecological role, one where blending into the forest mattered more than looking impressive. This colour profile also supports the idea of crepuscular behaviour, being active at dawn and dusk. In modern ecosystems, animals that move through low-light environments often have darker fur, feathers, or skin to avoid creating silhouettes that predators can track. If Ambopteryx launched itself between branches during the dim light of morning or evening, dark membrane wings would reduce the risk of being spotted mid-glide. The fuzz on its body would help manage heat loss during cooler periods of activity. Diet and lifestyle, night nibbler. One of the most thrilling and scary parts of Ambopteryx's story was finding out what it ate and how it lived its daily life. Paleontologists thought small Jurassic dinosaurs would have clean bodies, but this one didn't. It wasn't a bird of prey that hunted bugs like early birds. It wasn't a hunter with sharp teeth like small theropods. It also didn't eat food like some later gliding animals did. It was a shadow-dwelling, nocturnal or crepuscular climber that used short, quiet glides to catch insects, worms, and other small animals hiding in the forest overhead. This type of animal isn't found very often today. These days, ecosystems tend to specialise, but Ambopteryx seemed to have been designed to live in a way that was in between. It was a quiet generalist with a dangerous reach. The first clues came from its teeth. They were small, fine, and slightly recurved, not the slicing knives of predators, but not the blunt nubs of pure plant eaters either. The tooth pattern matches animals that eat soft-bodied prey, insects, grubs, larvae, small vertebrates, and perhaps even tree sap. CT scans of the jaws show weak bite force compared to most theropods, which rules out anything large or armoured. But the spacing and shape fit with quick, snatching bites. Combined with the gliding ability, this hints at ambush-style feeding. Glide across a gap, land silently, and grab whatever was resting on the bark or nestled in a branch fork. The claws support this idea. Their sharp curvature and wide gripping surface would let Ambopteryx cling to trunks while searching for food hidden under bark. Many modern climbing insectivores, including the aye-aye, marmosets, and certain woodpeckers, rely on claw strength to cling while probing for prey. Ambopteryx lacked specialized digging tools, but its elongated fingers suggest it could pry, hook, or scrape lightly, exposing worms or larvae. It didn't need power, it needed reach. It gets even more exciting when experts look at how a species' close cousins live. Several kinds of Scansoriopterygiids keep their stomach contents intact. One, Scansoriopteryx, has signs of bugs on it. Another one, Epidexipteryx, seems to have eaten soft-bodied animals and maybe even plants. These clues strongly suggest that the whole group ate both plants and animals, or mostly insects. Ambopteryx probably lived the same way as the other species because it has similar teeth and bones. It probably searched the mid-canopy for small animals and ate fruit, seeds, or sap to boost its diet. Its body proportions also point toward a slow, deliberate lifestyle. The large torso suggests room for a digestive system that could handle plant material. Even though it wasn't built like a full herbivore, it likely ate whatever was available: berries, leaves, insects, small reptiles, and even carrion when it stumbled upon it. Its energy needs were probably low. Gliding is cheap. Climbing is cheap. Staying still is the cheapest of all. A quiet life in the branches, moving only when necessary, would have allowed it to survive in a forest where predators like early tyrannosaurs and large raptorial dinosaurs prowled the shadows below. Patterns in its skeletal growth also tell a story. Bone histology shows slow, steady growth rather than the faster growth seen in some active, fast-moving dinosaurs. This aligns with creatures that avoid high-energy lifestyles. Ambopteryx wasn't built for sprinting or chasing. It was built for patience, the kind of patience used by nocturnal animals that sit frozen until their prey wanders into reach. Melanosome evidence hints it was active at dawn, dusk, or night, when insects are plentiful and predators are less alert. In that dim light, dark membranes and fuzz gave it camouflage, allowing it to glide unseen between feeding spots. The nighttime aspect becomes more convincing when considering its eye placement. While not as extreme as dedicated nocturnal animals, the orbit size leans slightly toward low-light adaptation. Big, forward-facing eyes help detect movement in shadows and improve depth perception for gliding. This would be crucial when navigating branches in poor light. Even a small miscalculation could lead to a fall, and falling in a Jurassic forest often meant landing near something hungry. Its eating habits were probably also affected by the threat of being eaten. Large animals below would be less likely to notice if they stayed high in the trees, moved slowly, and only glided short distances. In the cover, there was a safe area as well as a race. There were pterosaurs flying above. Early birds flew from branch to branch. Small mammals ran around in their nests. For an animal like Ambopteryx, the answer was easy. It just had to fill in the gaps between these two ways of life. Eat what other people forgot about. Move like no one else could. You should live in the small vertical slices of habitat, where no one else has all the benefits. Why it vanished? For all its strange brilliance, Ambopteryx did not make it past the Jurassic. Its entire lineage, the Scansoriopterygiids, disappeared long before the famous feathered dinosaurs of the Cretaceous took over the skies. And the more paleontologists studied its anatomy, habitat, and ecological pressures, the clearer the picture became. This was a creature perfectly designed for a specific world, and when that world changed, its entire flight system began to collapse. The question isn't why it died out instantly, it's how it managed to hang on as long as it did. Because evolution rewarded flexibility, and Scansoriopterygids were specialists in a forest that was slowly turning against them. The most significant reason they disappeared was that the forests were changed. These dinosaurs lived in the Middle Jurassic Yanliao forests, which were thick, wet and stacked. They made narrow, vertical passageways that are great for short runs. But around the late Jurassic, the temperature around the world changed. Some woods got thinner, others switched to different kinds of trees that were farther apart. It got harder for membrane gliders to find the tight, regular canopy lines they needed. If your way of flying rests on quick jumps between stems that are close together, then even small increases in tree spacing are terrible. Flapping gliders with feathers could move more. The pterosaurs could just fly higher. This wasn't an option for membrane-winged dinosaurs. Their plan for aerodynamics wasn't flexible. The sky changed along with the trees, and it wasn't for the better. The second major pressure came from rising competition. Early birds and more advanced feathered dinosaurs were improving rapidly. Their feathers became more aerodynamic, their tail fans grew more sophisticated, and their chest muscles strengthened. With each improvement, feathered dinosaurs gained better steering, better braking, and eventually true powered flight. They could reach food sources earlier, escape predators faster, and occupy niches that Scansoriopterygids once monopolized. Evolution doesn't favor the weirdest design, it favors the one that adjusts smoothly. And feathers, unlike stiff skin membranes, were endlessly adjustable. That flexibility allowed early birds to survive environmental changes that increasingly excluded membrane gliders. Predation also escalated. As the Jurassic progressed, more agile and specialized hunters evolved. Small mammal predators became quicker, larger paravians grew stealthier, even early tyrannosauroids entered the forests in some regions. A glider that needed perfect launches and controlled descents had little margin for error. One missed landing, one unexpected gust, one branch too far, and the glider dropped into a world full of jaws. Membrane-winged dinosaurs survived by living in a narrow vertical window. When predators began invading that same window, the system broke. Another critical factor was energetic inefficiency. While gliding is cheap, climbing is not. Scansoriopterygids relied heavily on climbing to reach launch points and feeding areas. As food competition increased, they had to climb more often, travel farther, and take more risks. Early birds, meanwhile, could simply flap to a branch without climbing every inch. This difference in energy budgeting became one of the slow, invisible killers of the Scansoriopterygid way of life. Evolution rewards those who spend less to get more. And once feathered flyers began doing that better, membrane gliders found themselves outclassed. Their reproduction strategy likely didn't help either. While direct evidence of Scansoriopterygid eggs is lacking, their small body size and lightweight skeletons suggest they laid small, fragile eggs and produced few young at once, much like other small theropods. This was fine in a stable canopy world, but in a shifting environment with rising predators and shrinking habitats, low reproductive output meant they couldn't bounce back after population crashes. Specialist species with narrow ecological requirements tend to disappear quickly when stressed. Ambopteryx and its relatives fit that pattern perfectly. What got misread and fixed? When Yichi was first named in 2015, a lot of paleontologists secretly wondered if the fossil was lying to them. The stylized rod that stuck out from its wrist looked really weird. The membrane marks didn't seem clear enough, and the thought of a dinosaur with wings like bats seemed to go against everything scientists thought they knew about how flight evolved. Some experts said it was clear that the strange wrist bone might be a piece of an animal that got lost. Others wondered if the wing membrane was really just skin that moved as it turned into a fossil. In short, a lot of scientists didn't believe what they were seeing. That doubt didn't go away until Ambopteryx showed up, which was almost exactly the same in every way that counted. The styliform part itself was one of the first things that people got wrong. When Yiqi was found, the bone looked like a straight rod sticking out of the wrist, but it was hard to figure out what the joint surfaces meant. Some thought it might be a rib that was out of place. Others said they thought the hardening happened because of cartilage. Some people even thought the rod might have belonged to a different animal that had combined with the specimen in some way. But when Ambopteryx was found, its styliform bone had better signs of how it fit together, including blood vessel marks and scars from where muscles had attached. CT scans showed that the structure inside was consistent with load-bearing stress. This bone wasn't just there, it was a real part of the body that held up the membrane wing. Another misread involved the membranes themselves. In Yiqi, the soft tissue impressions were faint and wrinkled, making it hard to reconstruct their shape. Skeptics argued that decomposition can stretch or fold skin, creating outlines that look like wings, even if none existed. But Ambopteryx preserved its membranes in crisp carbon film, with clear anchor points along the arm and torso. Under UV light, some portions fluoresced differently than surrounding rock, confirming they weren't decay artifacts. These twin fossils made it undeniable Scansoriopterygids had true patagia, functioning flight membranes. Scientists also misjudge the ecological context. Early interpretations imagine Yiqi as a poor flyer or even a ground-hugging animal that barely glided. But new biomechanical analyses applied to both species corrected this view. The shape of the styliform bone, the proportional arm length, and the preserved joint angles all pointed to a glider comfortable in tight canopies. Initial skepticism had underestimated its climbing ability and overestimated its need for open air. With both fossils showing nearly identical proportions, a clearer picture emerged. These were arboreal specialists, not evolutionary mistakes stumbling across the forest floor. Histology also exposed earlier misreads. Some researchers originally believed the styliform element was too fragile to support a wing. But thin section analysis revealed that the microstructure of the bone resembled strong, lightweight support structures found in bats and pterosaurs. Instead of being brittle, the styliform was reinforced internally, adapted to withstand the tension of a stretched membrane. This helped settle a long-standing debate. The wing wasn't accidental or useless. It was an intentional aerodynamic design. Fossil positioning caused even more confusion. In Yiqi, the arms appeared slightly collapsed inward, giving the impression of limited wing extension. But Ambopteryx preserved its limbs in a way that showed a greater range of motion. This proved the animals could spread their membranes more widely than the first reconstruction suggested. What was once seen as a stiff, awkward structure became a flexible gliding apparatus built for short, controlled flights. Even the fuzz and filaments around the body were misinterpreted at first. Some paleontologists thought they were plant fibers or contamination, not proto-feathery covering. But repeated microscopic analysis revealed melanosome clusters inside the filaments, biological structures, not debris. This corrected another misconception. Scansoriopterygids weren't naked reptiles. They were fuzz-covered, warm-blooded climbers with a unique flight system. The bigger pattern, evolution spams, prototype. When paleontologists agreed that Ambopteryx and Yiqi were real dinosaurs with real membrane wings, they came up with a much bigger discovery. It wasn't just these animals that were weird. They showed that evolution doesn't work according to a master plan, which is something that has happened many times in Earth's past. It prototypes over and over again, in a crazy and sometimes careless way. Most samples don't work, a few do well, And the fossil record only shows a very small number of these tests. There is a long, crazy list of genetic tests that were tried once, worked for a short time, and then disappeared when the world changed. The Scansoriopterygids are a good example of this. The Cambrian explosion is the earliest and clearest example. In that era, evolution threw out forms so bizarre they still look fake today. Opabinia, with its 5 eyes and trunk claw, Hallucigenia, with spines like a walking cactus, Anomalocaris, with its pineapple slicer mouth. None of these creatures left direct descendants. They were prototypes for body plans that didn't survive long-term competition. They worked in their moment, then disappeared when new predators evolved. The pattern repeats in the Devonian seas with armoured placoderms, like Dunkleosteus. Incredible jaw engineering, unmatched bite force, and a design that lasted only until the next mass extinction reset the oceans. The Permian brings another round. Sail-backed Dimetrodon, saber-toothed Gorgonopsians, enormous amphibians lurking in swamp rivers. Many of these lineages dominated their ecosystems, but failed to adapt when climates shifted or when early archosaurs appeared. Evolution didn't care that they were successful for millions of years. Once the environment changed, their specialized designs became liabilities. The Scansoriopterygids belong to this same lineage of evolutionary experiments, but they are unique because they were prototypes for flight, one of the rarest and most complex adaptations on the planet. Before their discovery, the story of flying vertebrates was simple. Pterosaurs evolved wings first, then birds, then bats much later. But Ambopteryx proved that dinosaurs themselves tried more than one path to the air. Feathers were one solution. Membranes were another. Both worked, at least for a while. But membranes, in this case, didn't win the long race. When paleontologists decided that Yichi and Ambopteryx were real dinosaurs with real membrane wings, they found something much more important. These animals weren't the only ones who were strange. They proved that evolution doesn't follow a master plan, which has happened many times in the history of the Earth. It prototypes over and over again, sometimes carelessly and sometimes in a crazy way. A lot of the tests don't work. Some people do well. And there aren't many of these tests found in fossils. There are a lot of crazy genetic tests that were only used once, worked for a short time, and then went away when things changed. One group that does this well are the Scansoriopterygids. The prototype pattern also explains why Ambopteryx didn't leave descendants, while feathered theropods did. Feathers could be repurposed for warmth, display, maneuverability, camouflage. Membranes, by contrast, were single-purpose tools. They either helped glide or they didn't. When conditions changed, there was nowhere for the Scansoriopterygids to pivot. The bigger picture is even more humbling. Every major group dominating Earth today, mammals, birds, reptiles, fish, comes from a lineage that survived while dozens of equally creative, innovative prototypes failed. Some of those failures were massive. Some lasted longer than humans have existed, but evolution is ruthless. It keeps what works, not what looks impressive. It wasn't just that these dinosaurs were strange that scared paleontologists. One reason was that they fit into a pattern that made me think we have only begun to study evolution. If a dinosaur with bat wings can die out and not be found again, how many other versions did the same thing but didn't leave fossils? What number of flight devices did not make it to the time when we found them? How many animals, reptiles, or frogs came up with traits that didn't last more than 1 million years before they went away? Why this fossil still haunts papers. Even after the shock settled, even after Ambopteryx and Yichi were fully accepted as real and not fossil pranks, one thing still lingers in scientific papers, conference talks, and review articles: uncertainty. And in paleontology, uncertainty is the closest thing to fear. This fossil, small, delicate and discovered in a quiet corner of northeastern China, didn't just add a new species to the books. It rewrote the rules about how dinosaurs experimented with flight, and it left researchers with a haunting question. If we were this wrong about something so important, what else are we missing? One of the factors that scares scientists the most about this fossil is that it makes them think about how messy early flight evolution was. For many years, scientists were sure that the story of dinosaur flying went like this: feathers, gliding, flapping, birds. On the other hand, Ambopteryx showed a different world where dinosaurs used styloform rods and skin tension instead of feathers to make wings out of membranes. That means flight didn't come about through a single evolutionary road, but through a lot of different tests, many of which didn't leave much of a trail. This realization is often used as a warning in science papers. Don't expect that things will go in a straight line. Don't think things are easy. There are biases and gaps in the fossil record. Another reason the fossil haunts researchers is the terrifying possibility that these animals were not rare. The Yanliao biota is one of the best soft tissue fossil sites on Earth. It captures details other environments never preserve: membranes, filaments, cartilage. So when we find two membrane-winged dinosaurs here, it raises the obvious question: were they truly unusual, or does every region with poor soft tissue preservation hide lineages we'll never see? Many paleontologists fear the latter. If so, our entire understanding of small dinosaur diversity could be skewed toward creatures with feathers only because feathers fossilize more often than membranes. The fossil also keeps resurfacing because it destroys the idea of inevitability in evolution. Most scientific narratives describe bird flight as if it were the unavoidable endpoint of dinosaur evolution. But Ambopteryx proves that evolution was not marching toward birds. It was throwing ideas at the wall. Some ideas, membrane wings, worked for millions of years, but ultimately disappeared. Others, feathered wings, happened to survive. This randomness, this sense of it could have gone very differently, makes researchers uneasy. If Scansoriopterygids had survived longer, or if forests had stayed dense, the skies of the Cretaceous might have been filled with bat-winged dinosaurs instead of early birds. Biomechanics papers continue to debate Ambopteryx because it breaks aerodynamic categories. It wasn't a typical glider because the stiff styloform rod limited maneuverability. It wasn't a typical flapper because the chest muscles were too small. And it wasn't a parachuter like some feathered dinosaurs because the membrane created real lift. This middle ground flight style doesn't fit into existing models. Scientists still run simulations, build wing replicas, and test airflow patterns, and the results often conflict with each other. The fossil refuses to settle into a neat aerodynamic box, which is unusual. Most extinct flight systems eventually make sense. This one still doesn't. The fossil also haunts because it exposes the limits of interpretation. For every detail paleontologists feel confident about, the styliform rod, the patagium, the climbing claws, there are 5 other details they argue over. How flexible was the membrane? How did it handle turbulence? How fast could the animal glide? Was it nocturnal? Did it hunt actively or forage passively? Each question spawns new papers, new debates, and new models that contradict earlier ones. Ambopteryx is a fossil that refuses to be fully understood, even with modern tools. A single fossil shouldn't have changed the story of dinosaur flight, but this one did, shattering a century of certainty and revealing a hidden world of evolutionary experiments that vanished long before birds ruled the skies. Ambopteryx, Yi-Ki, and their membrane-winged kin remind us that the past isn't a clean ladder of progress, but a maze of forgotten branches, dead ends, and bold designs nature tested once and never repeated. If this deep dive into prehistoric surprises left you wanting more, hit like, subscribe, and make sure you stick around, because the next discovery could rewrite everything we think we know all over again.